To calculate the total available watts per square foot, you'll use the formula total available watts per square foot equals total circuit amps times voltage divided by square footage. Let's break down how to apply this formula in the context of a telecommunications room. Firstly, you need to determine the total amps. Given the scenario of 920 amp single-phase circuits and 130 amp 240 volt outlet, you would calculate the total amps from the 20 amp circuits by multiplying 9 by 20, which equals 180 amps. Then, you add the 30 amps from the 30 amp circuit, resulting in a total of 210 amps. Secondly, you need to acknowledge the voltages. The 20 amp circuits operate at 120 volts each and the 30 amp circuit operates at 240 volts. When calculating the total watts, you consider the individual circuit voltages in relation to their respective amperages. Thirdly, calculate the total watts. Using the total amperage of 210 amps and a calculated voltage contribution that accounts for both 120 volt and 240 volt circuits, the process looks like this. You'll use total watts equals total amps times total voltage. This calculation isn't straightforward, as you cannot simply add 120 volts and 240 volts together and call it total voltage. This is because the amperages must be applied to their respective voltages. Instead, you need to calculate the wattage for each circuit type separately and then combine them. The 920 amp circuits at 120 volts each contribute 9 times 20 amps times 120 volts, equaling 21,600 watts. The single 30 amp circuit at 240 volts contributes 30 amps times 240 volts, equaling 7,200 watts. Adding these together, 21,600 watts plus 7,200 watts gives a total of 28,800 watts. Fourthly, determining the square footage of the telecommunications room is crucial. Without the square footage, you cannot complete the final calculation. Assuming you have the square footage, for example, let's say the room is 100 square feet, you would divide the total watts by the square footage to find the watts per square foot. In this example, 28,800 watts divided by 100 square feet would equal 288 watts per square foot. It's important to note that this calculation assumes all circuits are running at their maximum capacity simultaneously, which may not always be the case in a real-world scenario. The actual available watts per square foot will depend on the specific load connected to each circuit. Considering practical applications, you might also want to factor in a safety margin, reducing the calculated watts per square foot by a certain percentage to avoid overloading the circuits. Another consideration involves the National Electrical Code, or NEC. The NEC provides guidelines for the minimum requirements for electrical installations, including those in telecommunications rooms. Consulting the NEC, particularly articles related to branch circuits, feeder calculations, and communications systems, can provide additional guidance and ensure compliance with safety standards. For instance, NEC Table 220.12 provides general lighting loads by occupancy. While this table isn't directly applicable to a telecommunications room, it can offer a baseline for comparison. Furthermore, understanding the load characteristics of the equipment that will be used in a telecommunications room is essential. Different types of equipment have different power requirements and load profiles. Some equipment may draw a constant amount of power, while others may have fluctuating loads. Taking these factors into account will help you provide a more accurate estimate of the available watts per square foot and prevent overloads. Also, consider the voltage drop. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. The longer the circuit and the higher the current, the greater the voltage drop. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders. You can use voltage drop calculators or formulas to estimate the voltage drop in each circuit and ensure it is within acceptable limits. Moreover, consider the power factor. The power factor is the ratio of real power, measured in watts, to apparent power, measured in volt-amps. A low power factor indicates that a significant portion of the current is not contributing to useful work. This can increase energy consumption and stress the electrical system. Some equipment, such as motors and fluorescent lights, have low power factors. Power factor correction can improve the efficiency of the electrical system and reduce energy costs. Additionally, think about grounding and bonding. Grounding and bonding are essential for safety and to prevent electrical shock hazard. Grounding provides a low impedance path for fault current to flow back to the source, causing the circuit breaker to trip and to energize the circuit. Bonding ensures that all metal parts of the electrical system are at the same potential, preventing voltage differences that could cause shock hazards. The NEC specifies the requirements for grounding and bonding. In summary, calculating the available watts per square foot involves several steps. Firstly, determining the total amperage from all circuits. Secondly, understanding the voltage characteristics of each circuit type. Thirdly, calculating the total wattage by considering individual circuit contributions. Fourthly, dividing the total wattage by the square footage of the room, but remember to do the math correctly. Finally, consider safety margins, NEC guidelines, load characteristics, voltage drop, power factor, and grounding and bonding to ensure an accurate and safe electrical installation.